What is matter? So we're doing the study of matter. We should know what matter is. So matter is, in big generic terms, matter is stuff. Okay? Matter is stuff. But what makes something stuff? Well, it turns out that stuff is, anything that has stuff has two things in common. One is that it is anything that takes up space and has mass. Okay? Now, taking up space is not the hard part here. Taking space means that you can measure its length, its width, and its height. It's got a volume. Okay? Has mass. Mass is the stuff. Okay? And if you look up the definition for mass in your book, they will tell you it's a measure of the amount of matter in an object. But if you look at those two definitions, there's a problem. Matter has to have mass, but mass is how much matter you have. Seems kind of circular. So, well, that's a definition of mass. It's not the one that's going to do us any good right here. Okay? So here's my favorite definition of mass, and it seems a little bit strange because we think of mass as weight, but this is what mass really is. Mass is resistance to change in motion along a smooth and level surface. How much it would force, how hard you have to push to get it to move faster, or how hard you have to push to get it to move slower, or how hard you have to push to get it to turn. Okay. For example, we use mass and weight interchangeably because gravity affects mass. But when you go up into space, you lose gravity, but you don't lose mass. So that the astronauts, when they go out to do a spacewalk, they have to work extra hard. They can move things that would be really heavy, but it's actually a really difficult task. The first American astronaut that went outside the spaceship and went on the first spacewalk, when he got back, he was doing a couple of simple jobs just to see what it was like to work in space. That's what they were testing. And then he came to climb back into the Gemini capsule, and he was so tired he could barely close the door. The door required a manual handle to pull and lock, and he was so tired he could barely do it. And this is an astronaut. This is somebody who's in the peak of physical condition. If he's outside and everything's weightless, how do you get so tired? Well, what he found out was that it was weightless, but it wasn't massless. It still resisted changing its motion. So here on Earth, when we pick something up, and set it on a table. Okay? As we move it, once I set it on a table, it's just going to sit there. Okay? As I pick it up, I lift, and then I can stop lifting any harder because I'm holding it. But in space, you don't have any gravity. So once something starts moving, it's going to keep moving that way until you stop it. So you can't just set things down. Okay? If you push something heavy, you're going to have to push just as hard to stop it. So they found they were doing twice the work. So if you watch astronauts in space, you'll watch them move slowly. And that's because if you move really fast, that means you put a lot of force into getting something to move, and you're going to have to put that much force into getting it to stop as well. So when you go up into space, you lose weight, but you don't lose mass. So mass is, the more mass you have, the harder you're going to have to push to get it to change its motion. For example, which is harder to push down a road? A bicycle or a car? They're both rolling on wheels, so there shouldn't be much friction, but to get the car started, you got to push a lot harder. And if you want to stop the car, you'd have to push a lot harder to stop the car than you would to stop the bike. Why? because the car has much more mass than the bicycle. So here on Earth, we see that same resistance to change in motion. It becomes really apparent in space. So anything that has those two properties is matter. Okay? So is your calculator matter? Well, you can measure its length, its width, and its height. And if you throw it at somebody, you throw it at a curtain, it's going to push the curtain back. That means that while it's flying, it resists having its motion changed. So it'll move the curtain out of the way. It'll push on the curtain. So your calculator has mass and has volume. It's matter. How about the air we breathe? Is the air we breathe matter? Well, if I put it in a balloon, I could measure the volume of the air in the balloon. But what about mass? Does air have mass? Does air resist having its motion changed? Well, if kids, don't try this at home, but if you stick your hand out the window of a moving car, don't do that because you could lose a hand that way. If you do stick it out, it's going to push your hand backwards. That's because you're pushing on the air to get it going. Air resists having its motion changed. That's the idea behind a sailboat. The air is moving, it hits the sail, and it pushes the sail because it resists having its motion changed. So air has mass, takes up space, it's matter. Okay. What about light? Well, the light seems to fill this room. So you can think about it as filling up a room. That's kind of like volume. It's not the same as air, though. But the big difference is that if I want to stop light, all I have to do is stick a piece of paper in front of it. If you stick a piece of paper in front of a spotlight, a really bright light, does the light push the paper out of the way? Nah, it doesn't push the paper. So light is not matter. Light turns into the other thing in the universe that's not stuff. Light is energy. So everything in the universe is either matter or energy. Okay. So we're going to study matter. So now we know what matter is. What kinds of matter are there? Well, scientists most often try to get substances. Okay, a substance means it's all one kind of matter. It's pure. If you look at the individual pieces that make it up, the individual pieces of it are all the same. You know, everything's made up of atoms, molecules. In a substance, every molecule is the same. If it's not a substance, it's got one kind of matter, it's got more than one kind of matter, then it's going to be a mixture. Most of the things almost everything you deal with on a daily basis is a mixture. You deal with very few pure substances. I mean, the water that comes out of your tap, it's not pure. The closest you could probably come to pure water would be buying distilled water. Okay? So almost everything we deal with on an everyday basis is a mixture, which is a problem for a chemist because we're trying to do a control experiment, and I don't want to see the effect on a mixture of chemicals. I want to see the effect on one chemical. So chemists spend a lot of time purifying mixtures, separating the substances out so they can see the individual pieces. Because you don't want to study two things at a time. You want to study one thing at a time. So a word I'm going to use all year long is property. And property means something different in science. Okay? A property is a word that describes stuff. In English class, you called them adjectives. So if I asked you for a property of water, Well, water is a liquid. That's a property. Water is clear. That's a property. Water evaporates. That's a property. Okay? Now, there's two kinds of properties. Physical properties and chemical properties. Physical and chemical. Okay? And the difference, a physical property is one that can be observed without changing the substance. A chemical property can only be observed by changing the type of substance. So the in a physical we talk about a physical property, if it has that property, after you examine that property, it was still the same stuff. For example, water is clear. When I look at water to see that it's clear, have I changed the water into anything else? Nah. Look at a piece of paper. A piece of paper is white. By looking at it, have I changed what the paper is? Nah, I haven't changed it. So color would be a physical property. Chemical properties, when you're done observing that chemical property, you've made something new. Okay? So for example, a chemical property of this piece of paper is that it's flammable. Okay? That I can burn this. How would I know that that's a chemical property? Well, the only way to find out would be to light it on fire. And if it's flammable, it would leave something different when I was done. I'd have a pile of ash. So the property, flammability, is a chemical property. Now, color is always a physical property. Flammability is always a chemical property. Okay, here's the trick question. Okay, water is not flammable. The fact that water is not flammable, is that a physical or a chemical property? Well, you want to say physical, because when I try to burn water, nothing happens. But the question wasn't whether water burns. The question was whether the lack of flammability was a chemical process. The flammability is always a chemical property. It's one water doesn't have. Color is always a physical property. It's one water doesn't have. So it's the property that's chemical or physical. You either have it or you don't. Okay? So, I'm going to do a quick review, and then I want to tie it into that scientific method we learned earlier. Since third grade, you've been studying the states of matter. Okay? Okay? So what makes it this? So what makes something a solid, a liquid, or a gas? Well, let's look at their behavior. Okay? So all of them are matter. If I could just spell matter, I should say matter, that cannot flow. Flow means if you set it in a container, it's going to take the shape of that container. So if I put a solid piece inside a glass, a solid piece is not going to change to the shape of the glass. So those are properties that make something a solid. Okay, both solids and liquids have definite volume. That means you can't squeeze them or stretch them. But liquids take the shape of their container. They flow. I take my soda out of a soda-shaped bottle. I pour it into a cup. It becomes a cup-shaped liquid. Then it becomes straw-shaped. Then it becomes belly-shaped. It takes the shape of whatever container it's in from the bottom up. And a gas doesn't have a definite volume. You can squeeze a gas and make it smaller. You can stretch a gas and make it bigger. And gases are always going to fill whatever container you put them in. So they're going to take the shape of what container they are. Think about the air starts off lung-shaped, then it gets to be windpipe-shaped, then it gets to be balloon-shaped when you blow up a balloon. And you can squeeze that balloon and make it smaller. And you squeeze that balloon and change its shape. The fact you make it smaller means it doesn't have a definite volume. You can change its volume. And the fact that you can put a dent in it and it moves around tells you that it can flow. We're going to use another word that means the same as gas, and that is vapor. And vapor is when it's currently a gas, but it's normally a solid or liquid at room temperature. So somebody did something to make a gas out of it. For example, the high humidity we're feeling today is water vapor. Because water is normally a liquid at this temperature, but we can feel it dissolved, we can feel it mixed into the air. Because there's some humidity out there along with the heat right now. Okay. So, in summary, solids, okay? Definite volume. Do solids have a definite volume? Do they take up a certain amount of space? Can I squeeze them and if I squeeze them, will they get smaller? Yes. Well, they take up a certain amount of space. I can't squeeze them and make them smaller, so yes, they have a definite volume. Liquids. Do liquids have a definite volume? Yeah. I can't. Think about it. If liquids didn't have a definite volume, don't you think that Coke and Pepsi would try to, when you went to go buy a 1 liter bottle, they'd try to stretch it out? Okay? No, the reason why we sell sodas by volume is you can't change the volume. Okay? Unlike a gas where you can change the amount of space it takes up. So notice they sell they sell liquids by volume. Okay? They have a definite shape. That means they have a shape that they keep no matter where you move them. Well, a solid? Yeah, a solid doesn't change shape when I move it from one side of the table to the other. Does a liquid have definite shape? No. It takes the shape of whatever container it is from the bottom up, and gases fill the whole container. Okay, what happens to their size when you increase the temperature? Well, if you increase the temperature of a solid, usually they expand a little bit. There are a few things that get smaller, but usually when you increase the temperature of a solid, it expands. I use this for getting the lids off of jars. If you run them underneath hot water, the lid will expand and loosen up so you can get the lid off the jar. Liquids behave just like solids. They expand a little bit when you heat them. And in these cases, by a little bit, I mean 1, 2, 3, 4, 5%, not very much. Gases, on the other hand, gases have a large expansion. You can, if you heat a gas, it can double in size, triple in size, be 4 times the size. If you cool them down, they can get smaller and smaller. Okay? Another way to look at them is, can you make them smaller? Can you just squeeze them and make them smaller? Solids you can't. Liquids you can't. But gases you can. That's how your air shocks work in your car. There's a bunch of gas, and when you hit a bump, it compresses the air to keep it from, and that which gradually slows it down, so that you don't feel that full bump. Yeah. So, that's what they're like. People studied. You studied solids, liquids, and gases for a long time.